algebra. For the final two questions, problems 9 and 10. There are 30 pencils in a box. Some pencils were removed, and there are 12 pencils remaining. Using P to represent the number of pencils that were removed, which two of the algebraic expressions can be used to determine the number of pencils removed? Which two of the algebraic expressions can be used to determine the number of pencils that were removed? This problem may be solved by taking a simple step-by-step approach. We will take a step-by-step approach, dissecting the entire statement that we have here and separating it into useful components that will cause the problem to be easily solved. And that problem solving method that we are applying there, divide and conquer. 30 pencils in a box. Simply write down the number of pencils, which we say is 30. 30 pencils in a box. Step by step, building block approach. Some pencils were removed. If some pencils were removed, the pencils that were removed will be in such a way that the total number of pencils will be reduced. So of the 30, we will have less. That may be demonstrated by subtracting those that were removed. The pencils that were removed will reduce the number of pencils in the box. We therefore need to subtract that number of the sum that were removed. Will reduce the number of pencils altogether. Therefore, we will subtract the number of pencils that were removed. 12 pencils remaining. So we have 12 pencils in the end. There are 12 pencils there. So what will we do? The number remaining is the result of performing the operation that we have here. So if we have 30, we remove some. The number that remain will be the result of subtracting some of the pencils from the 30 that we had in the beginning. 12 is what remains. 12 is the result of taking some of the pencils out of the box. Using P to represent the number of pencils that were removed. How many pencils were removed? P. Using P to represent the number of pencils that were removed. So some pencils may be replaced by P because P represents those that were removed. So 30 minus P is equal to 12. And that is a statement that we arrived at by making use of the information that we have there. 30 pencils in a box. Some were removed. We have the others remaining. And that's all there is to it. Item B is one of the answers that we are looking for. Let's see what B says. 30 minus P is equal to 12. Just as we have it right here. So item B is no doubt one of the correct statements that we are looking for. So we have identified option B. But we need to identify another. We may arrive at another expression by transposing the equation. Since that equation is correct, the other one will be correct also, as long as the transposition process is correct. So this statement is correct. If we transpose correctly, we will arrive at another statement that is correct. Now, whether or not the one that we will arrive at is present in this set of options, then that is another question. We will eliminate negative p from the left hand side by the opposite of subtraction, which is addition. So we are actually about to transpose this equation, and in transposing the equation, of course, we have the equal sign right here being emphasized, because it is important to note that it is an equation for reasons that we will mention in a few seconds. So we are transposing this equation, and we have a negative p right there. We may eliminate the negative p on that left hand side by applying the opposite of subtract p. So there we subtract p to eliminate this effect. On the left hand side we need to add p, so we need to do the opposite of that subtract p effect. So we will eliminate negative p from the left hand side by the opposite of subtraction, which is addition. And we had the equal sign there emphasized quite a bit for a long while. Why do we emphasize it? We have an equation, that's why. But what are the consequences? Both sides are equal. Any adjustment that we make must be done in order that both sides are equally affected. So we have affected the left hand side by adding p, intending to eliminate the negative p from this side. However, by adding p on this side, we also need to add it on the other side. For an equation, we need to do the same thing on either side in order that it will remain consistent. So on the left hand side, negative p and positive p, the subtract p and the addition of p, those will have a cancelling effect on each other. Because they will have a cancelling effect on each other, p will be eliminated from that left hand side. P is eliminated from the left hand side, so we have 30 there. 30 is what is going to be there. Only 30, since the p is eliminated. But on the right hand side, we have 12 plus p. Wishing to eliminate the negative p, we add p. Cannot add p to one side, we add it to both. On the left hand side, the p's will have cancelling effects on each other. P will be eliminated on the left hand side. On the right hand side, we retain 12 plus p. If we write the expression in reverse, it is still correct. Notice that here we do not have any option that is similar, that is alike this one. That's what we imagine. However, this is an equation. So if we write the expression in the reverse order, then it is still correct. So switch that around. We have 12 plus p is equal to 30. So 12 plus p is equal to 30 right here, and that is option E. The other correct option is therefore option E. Why all of these pencils? We have quite a few pencils there, although I did not count them. Let us say that there are 30 of them in all. Let us remove a certain number of the pencils that we also do not know. So let us remove P pencils. P pencils were removed. So let us remove P pencils. The number of those pencils removed is called P. There are 12 pencils remaining. If we add the number of pencils removed to the number that remains, how many pencils will we have in all? So we had 30 to begin with. We take away some of them. If the number that we take away were added to the number that remains, how many pencils will we have? That's very simple. We are just replacing the number of pencils that we took away. So we should have the same number of pencils. Just like in any other case. You have a certain number of items, you take away some of them. Those that you have taken away, you replace them. Then the number that you have there is equal to the number that you had in the beginning. Right. So when we take away P, what remains is 12. If we add the 12 and the P, what will we result in? The number of pencils that we had in the beginning. See? We take away P, we replace P. We will still have the number that we had in the beginning. So we should have the same number that we had in the beginning, which is 30. 30 pencils. We will have 30 pencils if we take away some of the pencils and replace them. It is as if we did not take away any at all. And that is the expression that we had for option E. So we are sure that option E is the other option that we were looking for. The table shows a pattern created with blocks. It has 3 parts. That problem. Complete the table by writing the number of blocks for each pattern. That's the first part. How many blocks will be in the 5th term? Then state in words the rule for the pattern. So the first one, that's what we have. The same number of blocks that we had in the first pattern, and that turned out to be 6. We're just placing there and counting them. 1, 2, 3, 4, 5, 6. So that's the number in the first pattern. The foundation of the pattern consists of 6 blocks. So that's your foundation. And then we are going to add 2 to it. Not add 2, another one. So we have 2 of them. The second pattern has 2 sets. 2 sets of 6. And that will give us 12. That's not rocket science. Now this third diagram, how many sets does the third diagram have? 1, 2, 3, 4. The third pattern has 4 sets. 4 sets of how many diagrams? 4 sets of how many blocks? 4 sets of 6 blocks. So that's 24 blocks. What about the third diagram? The fourth diagram has 8 sets. 8 sets of what? The fourth pattern has 8 sets. 8 sixes, 48. So that will have 48 blocks. So we have completed the table. Now, after completing the table, we are required to say how many blocks will be in the fifth pattern. Our greatest clue for finding the fifth term is in how the others were calculated. So let us take a look at how the others were calculated, and we will be able to tell the number of blocks in the fifth pattern. The first one, well, that's not the first one, but we have 2 times 6 equal 12. We are looking at the ones that were calculated, not the one that we had before, although we are going to include that eventually. So the ones that were calculated, 2 6s 12, 4 6s 24, 8 6s 48. There is no calculation for the foundation term, and that is why we have not included it in the first set, but we are going to include it eventually. All other terms are multiples of 6. 6 is also a multiple of 6. So the foundation term, which contains 6 blocks, is 1 multiplied by 6. 1 multiplied by 6. The number that we multiply the base number by is being doubled each time. So it begins at 1. It is doubled to 2. Then it is doubled to 4. Then it is doubled to 8, as we can see over here. Then if it is doubled to 8, then the next one must be doubled to. We will see that in a while. So 2 is 2 ones, the 4 is 2 twos, the 8 is 2 fours. To find the next number that we should multiply by, we need to double 8. So we double each time. So we double 8. So 16 is equal to 2 times 8, and 16 will be the number that we multiplied by, that we will multiply by for the fifth term. Notice that we are multiplying by 2 each time. So this is doubled to 2, this is doubled to 4, this is doubled to 8, so the next one must be doubled to 16. And those are the numbers that we are multiplying by, but the size that we have here, which is 6, which represents the number of blocks in the basic pattern, is 6. It does not change. It is consistently 6. So in the fifth pattern, we will have 96 blocks. The fifth pattern has 96 blocks. A much simpler way to arrive at the answer is to realize that the pattern begins at 6. It begins at 6 because there are many ways that we can take a look at it. When we have a particular pattern, you know, students might take a variety of approaches to it, and it might be well based on the student's interpretation of the problem. So a much simpler way to arrive at the answer is to realize that the pattern begins at 6. Each subsequent pattern is then doubled. So each subsequent term is the double of the previous term. So we double 6, we have 12. We double 12, we have 24. We double 24, we have 48. So we need to double 48. The next term will be what we get when we double 48. And we will finish up by stating in words the rule of the pattern. The rule for the pattern begins with 6. The next term may be found by doubling the present term. We may develop a more sophisticated rule, and we may do that algebraically. Let us look at the sophisticated rule that we may develop. 1 times 6 equals 6. 2 times 6 is equal to 12. 4 6 is 24. 8 6 is 48. 16 6 is 96. The numbers that we multiply by are all powers of 2. 4 is 2 times 2. 8 is 2 times 2 times 2. 16 is 2 times 2 times 2 times 2. Because of the two occurrences of 2 multiplying together, 4 is 2 raised to the power of 2. 8 has 3 occurrences multiplying together. 8 is 2 raised to the power of 3. Or the third power, 16, is therefore 2 raised to the power of 4, or the fourth power. So put in those powers of 2. Two is just a single occurrence of 2. Right? 2 is just a single occurrence of 2. It's just 2. 2 raised to the power of 1. Any number raised to the power of 0 is equal to 1. So right there we will put the other powers. The power of 2 that 2 is 2 to the power of 1. And the power of 2 that 1 is 2 to the power of 0. As a matter of fact, any number we raise to the power of 0, the result is 1. Any number raised to the power of 0 is 1. So 2 to the power of 0 is 1. And that is what this 1 represents. The 2 is 2 to the power of 1, 4 is 2 to the power of 2, and so on. We may write the term by making use of the powers of 2 now. So write the terms by making use of the powers of 2. So this one is 1 times 6, 2 to the 0 times 6. 2 times 6, 2 to the power of 1 times 6. And we are multiplying in each case by powers of 2. 0, 1, 2, 3, 4, and so on. The rule therefore becomes 2 raised to the power of n multiplied by 6. And that is where n is the set of integers beginning at 0 and increasing by 1 each time. We begin at 0 and we increase by 1 each time. That is, we are increasing the power by 1 each time, beginning at 0. And those are the numbers that we are multiplying the basic number by, because the basic building block of all of those patterns is the original pattern that contained 6 blocks. So the algebraic representation of the rule is 2 to the power of n times 6. If we do that, then we will have all of the terms that we had on the previous slide. All of the terms, which are 6, 12, 24, 48, 96. And we just say 2 to the power of 0, 1 times 6 is equal to 6. 2 to the power of 1, that's 2 times 6 is equal to 12. 2 to the power of 2 times 6 is 4 times 6, which is equal to 24. And we are going up by powers of 2 each time. And that will be our rule. Now, just like the previous one, we seem to have arrived at the end of not only this audiovisual presentation, but the end of the entire set of presentations in a hurry. But for the last 2 audiovisual presentations, the requirement was much less than the others. You know, we are not going to have maybe an hour and a half or an hour 20 minutes for this audiovisual as we had for the others. For the algebraic representations that we have, we had for you the transfer of a statement to an algebraic statement, and we see that the algebraic statement can be arranged to form another statement. For the final presentation, which is problem number 10, the one that we have just completed, we realize that a pattern can be interpreted in many different ways. And the pattern, the last attempt that we made at it, is to arrive at an algebraic representation of it. But we can also give a description of the pattern in words. And I hope that you have some appreciation of the presentation that we have made in terms of using powers of 2 and generating the entire pattern of numbers.